Yes, very good morning. Today we try to solve a problem based on fifth unit, that is stability analysis. Stability analysis, we may come across several situations. So in our syllabus, we have a conventional method to solve our power system. That is with the help of our equal area criterion, swing equation. There are a lot of methods to solve our power system stability. The given case is one of the stability based problem. It is quite useful in your analyzing of your power system circuits. Yes, and the question is a three-phase fault occurs at the middle of the line 2 is cleared by isolating the faulted circuit from both ends. Your generator is delivering 0.8 per unit power at 0.8 power factor lagging. The fault is cleared in 0.1 second. Obtain the numeric solution of the swing equation up to 0.15 second using modified Euler method and Runge-Kutta method with the step size of del t equal to 0.05 second, and you take your inertia constant h as phi. So based on the given problem, we may draw a single line diagram. In some cases, the single line diagram is given in the problem itself. So here we have generator. So generator transient reactance is given, that is xd dash equal to J0.2, and the terminal voltage of the generator is given 1 at angle 0, and your transformer value J.1 is given, and transmission line J.4 is given, and voltage V is given. Based on the single line diagram, we may draw a reactance diagram. So E dash is unknown to us. The E dash is connected with your generator reactance, that is J.2, and from the J.2 we have ET. From your terminal voltage, this current is circulating, and our transformer reactance is J.1, which is given in the problem, and transmission line is two parallel transmission lines, each having J0.4, and at the end of the transmission line we have infinite bus. Its voltage is V at angle 0. Here we have to use our calculator in radians mode. So your terminal voltage of the generator, we generally assuming as 1.0 at an angle 0. So your P, which is equal to 0.8, cos pi equal to 0.8. We may approximate, that is the value of power and the power factor which is given in the problem, which is 0.8 per unit as your generator delivering power, and power factor is nothing but 0.8. So based on your power factor value, we may find out what is your angle of your power, that is phi equal to cos inverse of 0.8. We may utilize in our calculator and determine J0, 0.644 radians. So here we may construct a triangle with an angle of phi. The P value is known to us. So P equal to 0.8 per unit. Q is unknown to us, and your P and Q is adjacent by opposite, which may get hypotenuse is nothing but tan phi, which is given by Q by P. Q is unknown and P is 0.8. So from this equation we may write our Q equal to P dot tan phi equal to 0.6. So your P is 0.8 tan, and phi value is 0.644 radian. So we may substitute, we may get 6.6, and I equal to P minus JQ by ET conjugate. P value which is given in the problem, power delivering 0.8, and reactive power we determined previously, that's nothing but J.6, and ET conjugate is 1 times 0.8 minus J.6, and your generator voltage E dash, which is given as ET plus JXD dash I. Here ET we generally assuming 1 at an angle 0, and JXT is given J.2 into your current is nothing but 0.8 minus J.6. So when we substituting these values in our calculator, we may get 1.13 at an angle 0.412, which is equal to your generator voltage at an angle beta. Make a note of it. This value of E dash, which is equal to modulus of E dash at an angle beta. And second, we need to find out what is our infinite bus voltage. So from your ordinary calculation, we may write ET minus J X transformer plus X line into I, and ET is nothing but 1.0 at an angle 0 minus your transformer and transmission line reactance. I am taking J as common. So transformer is 0.1 and transmission line is 0.4 into 0.4 divided by 0.4 plus 0.4 into your current is nothing but 0.8 minus J.6. When we simplifying the value of the V equation, we may get 0.854 at an angle minus 0.285 is nothing but modulus of V at an angle comma. From these two equations, that is E dash equation and V equation, we may get del which is equal to beta minus gamma. Beta value is nothing but 0.142 and gamma value is nothing but minus 0.285. So when we subtracting these two values, we may get 0.427 radians. So based on this basic assumptions, we may determine our E dash equal to E dash at an angle del is determined, that is 1.13 at an angle 0.427 volts. So it is our basic values which we needed for our calculation. So here we have three type of calculation is needed. One is our pre-fault condition, what is the nature of the system in the pre-fault, and second case, what is the nature of system during the fault, and third one is what is the nature of system in the post-fault. Here your total reactance when you're pre-fault, we may have our general reactance diagram. In order to find out our equivalent reactance, we may short circuit our voltage sources and open circuit our current sources. From we simplifying, we may get it is 0.2 is something but generator, at 0.1 is transformer, and 0.4 into 0.4 is your two parallel transmission lines. When you simplifying these equations, this values, you may get 0.5. So we know that the power in the pre-fault condition is PE1 is nothing but a modulus of E dash modulus of V divided by X1. Here the X1 is nothing but the total reactance present in the pre-fault condition into sine del. Here your E dash is 1.13 into 0.853. That is E dash into V I am multiplying, and your total reactance is 0.5 into sine. I am equating your del equal to del naught, because in your pre-fault case, your del which is equal to del naught, which is equal to 0.8, and del naught, from this we have to calculate our sine del naught. Sine del naught is nothing but 0.414. From this we may easily find out del naught equal to sine inverse of 0.414 sine inverse, which is nothing but 0.427 radians. Yes, the first case is over. That is from your pre-fault case, we may solve easily. And next one is during fault condition. So when will your fault is occur? So when the fault is arrived at the time of your power system, the second transmission line, that is clearly it is mentioned in the problem. A three-phase fault occurs at the middle of the line 2 is cleared by isolating the faulted circuit simultaneously from both ends. Yes, at the middle of the line 2. So line 2 middle we have a three-phase fault. Yes, so only here I am indicating the second line. Your J4 ohm line is divided into, when the three-phase fault inferred in your power system, the J4 line is divided into two portions, that is J.2 and J.2. The reactance diagram which is given as, that is modification of during fault, we have reactance diagram E dash J.2 J.1, and the J.2 line and J.2 line, it is lying to ground. So when the two lines is lying in the ground, we have a delta like formation in the circuit. So what we trying to do is we have to convert the J4 ohm, J2 ohm and J.2 ohm delta network into star network. It is possible using your classical circuit theory. When you converting your delta to star, you may get J.1, J.1, J.5, J.2, J.1. So when you reducing these values here, J.2, J.1, J.1 is nothing but J.1, and here the middle of the that is mutual coil, we have J.05 and parallel to J.1. Again you have to convert the entire star into delta again. So when you convert your star into delta, you may get equivalent reactances J.1.3. So here the power obtained in the faulted cases P maximum of 2 sin del is nothing but E dash V divided by X2. X2 is nothing but total reactance when we have your fault. So 1.13 into 0.84, 1.3 into sin del. When you simplifying these values, you may get P2 equal to 0.742 sin del. So in the last case, we have a pre-faulty case, your circuit diagram for the post-fault condition. So we need not consider our second line here. We need not consider the J.2, J.2, whatever it is splitted. We need not consider the line. Without considering the line, we may have E dash, B, J.2, J.1 and J.4. So it is a pre-fault condition of the circuit. We may easily find out the total reactance is nothing but 0.7. And P3 here is given as E dash. Here it is E dash V by X3 sin del 1.13, 0.84 divided by 0.7 into sin del, which is given as 1.378 sin del. So so far we find out the power system in the faulted case, pre-fault case and post-fault case. So first case we have to utilize our modified Euler method. So during our fault, your PE equal to 0.742 sin del. So which is determined using your pre-fault case, and omega not equal to 2 pi f, which is nothing but 2 pi f is nothing but your supply frequency. In our Indian country we have 50 hertz, and some other countries they are utilizing 40 hertz or 60 hertz, but our standard supply frequency is 50 hertz. So 2 pi into 50 is nothing but 314.15, and del naught, which is we obtained it in the first case, that is 0.427 radian, and the step size is given in the problem, del t equal to 0.04 second. First we go on to the first iteration. So at the beginning of the first step, we have to consider a time which is equal to 0 at your d del by dt del omega naught is nothing but del omega naught equal to omega naught minus 2 pi f. So 314.159 minus 314.159 equal to 0, and d del omega by dt at del naught is nothing but swing equation at the initial case. So initial case in the sense when your time equal to 0, we have pi f by Hudson Pm dash minus Pe del naught. So pi into 50 divided by 5 minus your Pm dash is nothing but generated delivering 0.8, and Pe del naught is nothing but 0.742 sine 0.27, which is equal to 15.479. So at the end of the first step, at a t equal to 0.05, so the predicted values of your del and del omega naught of P is nothing but, so del 0.05 of P equal to del naught plus d del by del t, del omega naught into del t is nothing but, here del naught we find out as 0.427 in the pre-fault case, and d del by dt del omega naught, which is given as 0 here, into del t. Del t is nothing but 0.05. When we have 0 into 0.5, it will be cancelled out, so 0 only. We have only 0.427, so 0.427 is nothing but del 0.05 of p. Next we have to find out del omega 0.05 of p is nothing but del omega naught plus d del omega by dt into del naught into del t. Here del omega naught is 0. Here we found out here del omega naught is 0. So d del omega by dt del naught is nothing but 15. So 15.479 into your delta is 0.05, you may get 0.774 radians per second. So derivatives at the end of t equal to 0.05 is nothing but d del by dt del omega p 0.05 equal to del omega 0.05 of p. So nothing but again 0.774 radians per second. And next we have d del omega by dt equal to del 0.05 of p equal to pi f by h pm dash minus p del 0.05. Here they are neglecting that sign, but we have to introduce our sign also. P is sin del 0.5 of p. So pi into 50 divided by 5, 0.8 minus 0.742 sin 0.427, nothing but 0.479 radians per second. The corrected values. When you have your actual values, we have to use your corrected values. So corrected values are average value of two derivatives, nothing but del 0.05 of c. C denotes your corrected, and del naught plus del t divided by 2 d del by dt del omega naught plus d del by dt del omega 0.05. So here 0.04 0.427 plus 0.05, that is del t, into 0 plus 0.774 something but 0.446 radians. Then del omega 0.05 c is nothing but del omega naught plus del t by 2 d del omega by dt del naught plus d del omega by dt del 0.09 t. It's nothing but we have 0.774 radians per second. So at the end of the hydration we may have a corrected angle and corrected frequency. So next we have to proceed with your t equal to 0.05. So t equal to 0.05, I may go on to the second step. So in the second step, my d del by dt del omega 0.05 c equal to del omega 0.05 c is nothing but it is the values previously repeated 0.774, and d del omega by dt is nothing but del c 0.05 is nothing but pi f by h pm dash minus p is del 0.05 c, and pi into 50 divided by 0.8 and 742 sine of 742 sine of 0.06 omega 15.037.